My name is Seth Lloyd. I'm professor of quantum mechanical engineering at MIT. I've been working on ideas in quantum information ever since 1984, when I was doing a master's in philosophy of science at Cambridge, studying quantum mechanics and information, and taking Stephen Hawking's course on quantum gravity. And I became interested in the field because I thought that maybe if we studied the role of information in the universe, we could solve some of these difficult, outstanding problems in quantum mechanics and gravity and the universe as a whole. It turned out we still haven't solved them, but that's how I began.
Nice. And so from physics, then you moved to computing in a way. So how and when did you start to think in computing terms?
Well, because I was already thinking about information, which was about bits, the distinction between 0 and 1, or in the quantum mechanical case, an electron spinning up or spinning down, or electron here or over there, each of those being a bit, then it's natural to think about computation and information processing. A bit flips, the electron flips from up to down, the electron moves from there to there, electrons interact with each other. So during my PhD at Rockefeller University in New York, I started looking at ideas of information and computation. There were just a very few papers about this notion at that time by Richard Feynman and David Deutsch and a few other people. And around 1990, I thought maybe it's possible to build a quantum computer, because up till then they were just completely abstract ideas. In fact, Feynman said, I have no idea how one might build such a thing. And so in the early 90s, I started looking about how you could tickle atoms or electrons with light. And if you kind of tickle them in the right way, then they will flip. And if you make them interact in the right way and then tickle them some more, then they will perform quantum logic operations. And so by 1993, I'd worked out the basis of how you could build a quantum computer using off-the-shelf components like atoms, electrons, lasers, quantum dots, that kind of thing. And actually, during this time, I had a terrible time trying to get a job because ideas in information and quantum mechanics were regarded as very suspect because they had to do with foundations of quantum mechanics, which was thought to be a bad thing to work on. And so the only job I could get was not in physics, but in mechanical engineering. And at MIT, they hired me as a professor of mechanical engineering. And I got there in 1994, and right at that time, Peter Shor discovered his famous algorithm for quantum computers, how you could break codes. It was the killer app for quantum computers, killer with a Q. And then everything changed because then everybody became extremely interested in quantum computing. And because I'd already started to build quantum computers with friends who were doing experiments, then I started working closely with experimentalists to build the first superconducting quantum qubits. We did perform the first quantum algorithms using nuclear magnetic resonance with spins and molecules. And at the same time to work on other applications for quantum computers. And I've been doing that ever since.
So you have been one of the first working with the quantum computing, or at least quantum logics, if we can think about it.
When Peter Shor's famous algorithm for code breaking came out in 1994, the amount of interest skyrocketed. And I was already working with friends to build the first quantum computers and perform the first quantum algorithms. And then I was involved in many of the main technologies, such as nuclear magnetic resonance on nuclear spins, nitrogen vacancy diamonds, superconducting systems. I worked on the very early experiments for that.
You start to work on quantum algorithms in 1993. Does it mean that you were kind of the first? How that part developed, the quantum algorithms, even before the computers?
So in 1993, I wrote the first paper showing how you could build a quantum computer. And then starting after Peter Shor's famous algorithm in 1994, I started also working on algorithms. So I did the first algorithm that realized Richard Feynman's dream of having a quantum simulator, a quantum information processor where you could simulate anything, including the laws of physics at the most microscopic level. And then subsequently, I came up with colleagues to make the first algorithm for solving systems of equations, differential equations, which greatly expanded the realm of what quantum computers could do.
And so, how was the environment at the time? Because you guys were all at MIT, a few rooms away or few buildings away, and kind of working on the same things, but with different approach: mathematics, physics, computing, if you want, logics, if not even science and philosophy. So, how did you guys collaborate, or you didn't have to collaborate? Maybe things were just happening.
Well, for building quantum computers, it was easy because MIT is a great place. You go down, you say, I want to talk with the world's greatest experts in quantum dots. And, maybe we could build a quantum computer with quantum dots. And you go down the hallway and you talk to Ray Ashuri and he says, oh, what's a quantum computer? Oh, we can do this. And then you start doing the experiments. So for many of these technologies, that was great. For the theory part, actually, since we're talking here in Torino, there was a series of workshops here in Torino in the 1990s at the Institute for Scientific Interchange, where all the people in the field, meaning all 20 of them worldwide, came together and started talking about quantum algorithms with people like David Deutsch, later Roger Penrose. And so we worked on those here and all over the place. It was a small field. There were not many people. And also, because it had not been a very popular field before, we all were looking out for each other.
Nice. So in this documentary, I am not looking much into the computing and the hardware, and well, we know there are many techniques now to do this kind of quantum chips, or at least we are working around that. I am more looking at actually quantum information,
right,
and specifically in quantum math.
Right.
Now I don't want to get in the specific math. But the question is, do you think that by researching and working around this field, there will be a new form of math? And by that I mean kind of number systems and new ways to make equations, yes. But it can also not be actually about the hardware itself, but it's actually by working on this, we are going to discover a new logic, and then we can use that logic with maybe the hardware we already have today. Do you think that's a possibility?
Yes, one of the most fun parts about the whole field of quantum information is that the theory and the experiments have been advanced very rapidly together with a feedback with each other, which is how science works. And the idea that you could do logic at a quantum mechanical level was first proposed by David Deutsch in the 1980s. And then the mathematics of how you do quantum computing, quantum information, and also very importantly, quantum communication, because light is made out of photons, and we communicate using photons, and sound. Sound is made out of phonons, particles of sound. Those are very important. And the development of the math that goes behind quantum information happened quite rapidly. And the beautiful thing about this math is it's very simple. So it doesn't require calculus. You can easily teach it to smart high school students who can then make their own advances in the field. And this mathematics, this quantum language of computation, turns out also to be the quantum language of nature. And so quantum computing, this math of quantum information processing, allows you to understand how electrons hop around in a semiconductor, the possibility of making new materials, how particles collide and make new particles in a particle accelerator, as in CERN, and maybe even how the quantum mechanics of the universe as a whole fits. So in a sense, even without the the technological advances of building quantum computers, the mathematics that's come out of it is very beautiful and given us an entirely new and different understanding of how the universe works at its most fundamental level.
So that's exactly where I wanted to go. So do you think the breakthrough might be not in computing and not in making the chips, but actually might be in mathematics? Because eventually we figure how to get to big numbers in a much easier way, to compute big numbers in a much faster way. And that is going to be the real breakthrough. And that actually, in the history of electronics, but not only, already happened in a way, right? Because it took a very long time to get to the transistor. But then when we figure how to use a transistor and how to make a transistor, we got to the chip in 10 years, not even. This is again about the hardware, but I am really much interested in this kind of new mathematics, also as you call it. So do you think we might get to a point when we discover that new form of math that's much easier, is already everywhere, but we just didn't know how to use it yet?
So it turns out that the mathematics of quantum mechanics, the quantum language of nature, simple though it actually is. And by the way, when I say simple, it doesn't mean it's easy to understand, because quantum mechanics is weird and counterintuitive. Electrons can be here and there at the same time. You have funky effects called entanglement, where this electron seems to know more about this electron than it possibly should be able to know. But the math is simple. And then this allows us to understand not only the physics of nature, but has led to advances in pure mathematics and understanding, for example, how knot theory, how you tie things up in knots, how you could disentangle the knots. And in this fundamental mathematics of how quantum fields work, which turns out to be very difficult to understand. So this, and of course in quantum gravity, which is a very difficult mathematical problem. I would like to say that we're going to attain some amazing mathematical breakthrough, but those are hard to predict.
Sure, but yeah, I was asking that because now we go to the real core of the interview and the topic, which is cryptography.
Right.
And especially public key cryptography, and especially RSA, and this kind of cryptography that's based on a very particular math function, an assumption, a sort of open question, actually. Well, maybe it's forever, we don't know. And it's the factoring problem.
Yes, so the public key cryptography is based on this problem called factoring. So if I take two prime numbers, like 3 and 5, and I multiply them together to get 15, the factoring problem is, given 15, what are the two prime numbers which multiplied give 15? Now in the case of 15, that's not hard, because you just go through your prime numbers till you find two that are multiplied together get 15. But if your two prime numbers each have 100 digits, and then you multiply them together to get a 200-digit number, then there are way too many prime numbers to go through one by one to see if multiplied together they give you this 200-digit number. And factoring solves that problem very remarkably. That doesn't mean that there might not be another way to solve this problem without a quantum computer, but nobody's ever found one.
Do you know the book of the Structured Scientific Revolutions?
Yes, by Thomas Kuhn, who was at MIT. Yes, of course I do. Yes, I read it when I was a teenager.
Yes, and to me that is very interesting because it kind of relates to this problem of the factoring problem. Like really, that everything has been done to prove that that rule is valid, and there is no other way to get around it. And all the way to measure it and test it are made basically to prove the same thing. And because of that, we built all these other technological advancements and so on based on that principle. And I know that you are also passionate about the history of science and physics. And does it sound to you a similar situation that eventually, if that is proven to be false, then the whole society, society is so much based on technology today, might revolutionize itself because of that discovery?
Yes, so again, in cryptography, the notion is you wish to construct something that looks extremely random, but is not, right? That is, it actually was constructed by a very short key, and then you process this information to create something that looks random. Now, if it were the case, you could look at anything that looks random and find out how it was actually produced, find that it's not random. That would break all the codes that we have, not just public key cryptography, but all the codes. Now, at some level, if you're someone, say, from the National Security Agency who wishes to keep secrets, that's bad. On the other hand, if we could show that it's possible to take anything that looks random, that has a hidden pattern in it, and decipher that pattern, that would have amazing implications for human beings as a whole, because it means all kinds of hard problems would suddenly become easy to solve, and that would change the whole game.
Yeah, unfortunately, we have this cybersecurity issue, otherwise everything would be fine. Yeah, the situation now that we relied on this assumption for so long and so much without really considering that it was still a mathematical assumption, and so that maybe was a little bit naive considering the history of science and considering the history of math.
Yes, I don't think it's right to say that computer scientists are naive in this regard. They understand, maybe it's better to say that they're not naive, but they're frustrated. So they'd like to prove that it's possible to have one-way functions, but they can't. And they haven't been able to prove it, despite many, many decades of trying. So the cryptographic systems are based on the assumption that it's hard to do to break the code, which empirically is true. But we know that it might be possible to break these codes. Nonetheless, because secrecy and privacy are important both to people and to institutions, then we still use what we have. These codes might be broken in the future. When in 1995, I was at the very first meeting in the United States government to talk about the possibility of funding quantum computing. There were about a dozen people in the room at DARPA in Washington. And midway through the meeting, a mild-mannered mathematician stood up and said, "My name is Keith Miller. I'm from the NSA. And I'm authorized to tell you that the NSA is interested in quantum computing." And then he sat down. And everybody else was like, "Oh my God, I can't believe it. Somebody from the NSA actually told us something. Oh, what happened? What happened?" And it caused such a fuss that Keith got up again and said, "I believe I am also authorized to tell you this. Of course the NSA is interested in quantum computing, because our primary mission is to protect the secrets of the country for up to 30 years. So if right now we're encoding secrets that could be decoded within 30 years by a quantum computer, we need to know." And so, he said, actually, we would really prefer that it not be possible to build a quantum computer, because that would make our lives easier. However, if it is possible to build a quantum computer, then because of our secondary mission, he didn't say what his secondary mission was, but presumably it's breaking other people's codes. Because of our secondary mission, if it is possible, we want the first one.
Yeah. So that was 1995?
Yeah, I think in the spring of 1995.
And
possibly the fall of 1994.
Well,
plus or minus. Yeah.
Around that time. So 1995, 1994 is when Peter Shor made an announcement too, around that time.
Yes, so Peter Shor made his announcement, I think maybe in the summer of 1994. And then the people in the government who were interested in this got together, the small group of people who were working on this problem. And since I'd already proposed how you could build a quantum computer and was working on building them, then I was included in this meeting.
Can you tell me more about the meeting itself? Because so early in 1994 for a government meeting.
That's why I think I don't know if it was it was very shortly after Peter's announcement. So I'm thinking it might be early 1995. But those people at DARPA are in touch with what's going on.
Okay, yeah, the year is not even that much important. So it was organized by DARPA.
Yes, in conjunction with the NSA, because of course the NSA was very interested in this question.
So the NSA itself organized it too, or was co-organizing it?
It was coordinated. And then what happened was the first US government program to fund research in quantum computing came out of DARPA. And I was, my friend Jeff Kimball was the principal investigator, and I was a co-investigator on that grant.
Oh, wow, interesting. And well, now we know that actually NSA is building their own quantum computers, apparently, or they've been announced that they are having one, and they're also working on it. Well, going back to...
Well, but I mean, actually, they've been doing this for a long time. And I was, the sign that they're getting close to building a quantum computer is that all my friends would disappear and I wouldn't know where they were. But that hasn't happened so far. So my guess is perhaps they don't have one yet.
That actually reminds me of a question I usually do. Let's say that tomorrow you or a student or a colleague at MIT comes over and says, look, I figure how to solve the factoring problem. And what would you do? Because it's such a big and dangerous thing. I mean, first of all, you probably need to hide, right?
Yes, you should hide out while you figure what to do. And indeed, the public key cryptography algorithm, which is called RSA after Ravesh Shamir and Edelman, Ron Revester being a colleague of mine at MIT, Ravesh Shamir and Edelman discovered it only more than a decade after it had already been secretly discovered by the British Secret Service, who'd already been using it for at least a decade. And they hadn't told anybody, because why would they?
I know, which is so suspicious. But I talked about that with Ron, and he said that things were just in the air, But the thing is, so again, let's put in that scenario.
Right.
Whatever happens.
Yeah.
First of all, you hide, right?
While you think it through. Very good idea. You don't tell anybody, or only someone else who's willing to come and hide with you while you think it through together. Right.
While you're hiding and you're thinking through, then you need to figure who will be the first that will need to know about it, because it's key in so many critical situations. NSA, you would say, well, should I contact the government? But then do you trust your government? Do you trust the NSA? Or would you go first to, the financial people, or like the banking, which is also a critical situation? Or would you go to the human rights activists first? What would you do?
Well, obviously the most profitable thing would be to go to the criminals. This would be of tremendous value for people who wished to break codes. I actually do trust the NSA in the sense that, knowing what their mission is, they seem to behave in a very straightforward fashion to try to protect their own secrets and to try to find out other people's secrets. And their behavior my interactions with them over the years, though I've never done any classified research, is completely consistent with that. So I trust them in that sense. I don't trust them to tell me everything they know. In fact, I would be scared if it seemed they were doing that. So yeah, I don't know, it's a good question.
But the NSA could say, well, this is the only guy that figured it, so let's kill him. Something like that got revealed all of a sudden. It's kind of an issue because critical infrastructures, again, the financial system, transportation, the cryptocurrency world, everything would fall, right? I mean, everything would be also up for grab, by the way. It would be very chaotic, at least for a few months, or don't know.
Well, quite a long time, right? Because it's one thing, so for example, in the case of Shor's algorithm and RSA, what happened, and this is, by the way, one of the reasons why I think that the NSA, they don't know how, they don't have a quantum computer that can break these algorithms, and also they take it seriously. It was now quite a long time ago, I think maybe 10 or 15 years ago, the NSA said, okay, it's time to prepare for post-quantum cryptography because the chances of building a quantum computer are looking reasonably good. And so we want to have a new system in place before the old system can be broken. And that's just what's happened. Indeed, I note that some of the apps on my phone proudly boast that they're using post-quantum cryptography right now, though I don't know how much to trust them.
Yeah.
But never trust an app if you don't have to.
Yeah, I mean, I am following this post-quantum cryptography efforts, and most of people are very happy about that. And of course, it's great they are doing it, but we still don't know if they're safe because we don't have the computing there. With the cryptography has not been broken yet. We don't know how it will be broken, so we don't know how safe they will be. So far, they probably are, and more than the current cryptographic system that we have.
Yes, and I think this scenario where someone, if someone were to come up with a classical method for breaking RSA, which of course may already have happened, but I suspect not. In fact, indeed, for quite a long time, starting in the 1990s, the amount of money that the US government and the NSA were spending on quantum computing, which is a substantial amount of money that advanced the field technologically by a great deal. It was quite a lot of money, and it was enough money to suggest that they didn't know how to break RSA, but also it was just kind of the right amount of money to make people think that they didn't know how to break RSA, though they already did. So we had a kind of, in the quantum computing crowd, we had it's like speculations about whether that was the case. However, I think some of the whistleblower revelations that have occurred over the last 10 years indicated that that is not true.
Yeah. And when do you think this could happen? I mean, I know we were talking before, you said that you don't know if quantum computers will ever happen, but you're not talking about quantum computers. In terms of time frame, future time frames, yeah, maybe it doesn't happen tomorrow, but for when the public key cryptography system, current systems, or the factoring problem will be solved?
Yeah, for building quantum computers, I'd say, well, 10 years ago I said, 20 years plus or minus never meaning it might not happen. And indeed, the technological challenges are sufficiently great that it's very hard to even assign probabilities. So it's like, might happen, might not happen. Because the technologies have been advancing very rapidly. And similarly, the cryptographic techniques, the theory of, the error correcting codes have been advancing. But there's still a pretty big gap between them. So we still don't know exactly how to build a quantum computer that's error corrected that could break RSA.
But what about quantum algorithms? I mean, we had the quantum algorithm, sure, in 1994.
Yeah.
Maybe tomorrow a student of you or a colleague of you comes up with a new quantum algorithm, and that's going to break everything. You don't need the computing that. I mean, maybe you need 1 qubit. What about that? Could be also something, I mean, that's, we don't know because not even based on the hardware or the chip. It's really about just someone coming up with an algorithm in information, quantum information.
Yeah, that's a very good question. And indeed, just having 1 qubit that you can put in the state 0 turns out to be a surprisingly powerful resource in quantum computing. And there are problems that people believe can't be solved on a classical computer, where all you need is a completely messed up quantum computer in a random state and 1 qubit that is not, which is kind of remarkable. It's not currently believed that, nobody knows. When I say not currently believed, I mean nobody knows how, right? And also, there are reasons to think that it's not true that you could break these kinds of codes with just a much simpler quantum computer. just in the same way that the classical computer scientists have lots of, what they regard as good reasons to believe that that P does not equal NP, which is this very general problem of if you have something, can you have a one-way function where you put in a simple input, it creates a long, very random input, can you break that? That's this problem of whether P equals NP. And computer scientists tend not to believe that. They tend to believe that P does not equal NP, but I know some quite famous computer scientists, including Levin at Northeastern, who actually invented the whole distinction between P and NP. He said to Murray Gell-Mann and me, Murray Gell-Mann was my postdoctoral supervisor, the inventor of the quark, he said, "Oh, I believe P equals NP." And we said, "Really? Why do you believe that?" He said, and Levin said, "Oh, because the archetypical NP complete problem, which you would need to be able to solve to show P does not equal NP, is proving a theorem. Here's a conjecture. Is there a proof of this conjecture? And that's an NP complete problem." And Levin said, "I prove theorems all the time."
What is about the ethics of this quantum research, and especially potential quantum breakthroughs?
Yeah, so the ethics of quantum research is something I've thought a lot about, and it's related to the general problem of ethics of scientific research, because, look at really the whole worldwide contemporary boom in science came out of the huge amount of funding increase that the United States put into physics research, starting with the Second World War, in order to build the atomic bomb. So it would be very naive to think that a discovery of yours could not be used to do harm in the future, not just in quantum physics, but in chemistry and biology, etc. And my family are Quakers, or pacifists, and the only government funding I could get was from people like DARPA or the Army Research Office, and I was, should I take this? So I had a very good conversation with Johnny Wheeler, who was a famous general relativist, and he actually a somewhat politically conservative person, but very reliable. And he said, "Well, Seth, the research you're doing is completely open and is published and open to anybody. You're not agreeing to do secret research. Moreover, science is the most public form of knowledge, and that science is the knowledge which can, at least in principle, be verified by anybody. Doesn't matter if they're a man or a woman, or what country they're from, or even if they're human. They could be an AI or an intelligent alien or a rat, right? So that's public knowledge. That's what science is about. And in addition, Wheeler said, in a democracy, science is funded by the people, because the people regard this, through their representatives, as a good thing to do, because they see it as a public good, which actually it really is. So then, he said, the decisions about how to use the science that you produce, if you're putting it out there, is not up to you. That would be arrogant. Since you're creating a public good, it should be up to the people publicly, to discuss how it's going to be used and to see how it will be used. And moreover, there's nothing you can do about it anyway, because they're going to do that anyway. So, so I continued to worry about that. I didn't have to worry that much, because including from the last 40 years since I started working on this till now, even when there are lots of quantum computers, the most damage a quantum computer could do would be to fall off the lab table onto your foot. That would be very damaging. At the moment, they're too weak and not powerful enough to cause harm to cryptographic systems or pretty much anything else. But in the future, they might be used for that.
And so basically, breaking cryptography or trying to break cryptography is something we have to do anyway, even if it can cause damage, right? In a way. Just also to improve cryptography systems as well, but also because we cannot stop the scientific development anyway, even if it can cause something. I mean, that's pretty much what you said.
Yeah, people have been making cryptographic systems for thousands and thousands of years. And the earlier ones, like, well, you know, there's simple ciphers like the Caesar cipher where you just substitute one letter for another. And then there's these great devices like, I forget what they're called, but they're a cone, and you wrap paper around the cone, and then you write your message across like that. And then only someone with a cone of exactly the same size and shape can take your message and then wrap it around their cone and then read it. This is a Greek and possibly Babylonian device from thousands of years ago. So people have been making cryptographic devices and methods for thousands of years because there are some things that they prefer to communicate privately. Meanwhile, there are other people who would prefer to know what you're trying to communicate, and so they're trying to break these codes. So this has been going on, you know, for most of human history, certainly since the advent of writing, and it will continue to go on. And these methods are all imperfect, and all the methods that we've had so far, such of these methods, have been broken. And now actually public key cryptography in RSA has been broken if you had a quantum computer. And it may very well be that in the future that even with a classical computer that the methods we're coming up now can be broken. But as long as they're useful for people pro tempore, you know, at the moment, and for some period of time, then they will be used. And that's okay.